Thank you, Jan, very much. Yes, so our presentation will be slightly different than the previous seminar. So we have, I guess, 13 people briefly talking about their current research done at Sano and Healthcare Informatics Group. So here's the presentation overview. So we will start with basically applications of artificial intelligence in medicine, like more traditional image analysis and things like this, and then we will move towards more like virtual reality simulation, robotics, and other things. All right. So basically, Healthcare Informatics is a research group where we try to develop diagnostic and therapeutic processes on patient data extracted from images, and we basically, in other words, we would like to help clinicians to do their work to speed up the diagnosis, improve the diagnosis process, clinical care, but also surgery, including surgical training. So first person who will briefly discuss their work is Michał Grzeszczyk. Michał, please.
So hello, I'm Michał Grzeszczyk and I'm a PhD student here at Sano, and I'm here since November last year, and since then I've been working on a couple of projects. The first one was Smart Work for Smart Life. That's the project that is led currently by Aneta Lisowska, and it's quite interesting one from the perspective that all of us have either smartwatches or smartphones. Therefore, the main idea behind this project was to evaluate the technology and evaluate our possibilities in assessing positive and negative effect of our participants. So we wanted to check whether by collecting the physiological signal, the PPG signal that you can see here at the top center, we could somehow assess how our participants have felt at the specific moment. But Aneta has her seminar in the next week, so that's just a short teaser of what you're going to hear as well. So I invite you for the next seminar as well. The second project I was involved in was BabyNet. That's the project that we were doing with Szymon Płotka, and in a couple of slides Szymon will also tell you something about it. But the main idea was that we wanted to predict the birth weight just before the delivery, and it's important from the perspective of the fact that the weight has an impact on the type of delivery. So doctors can choose whether there is going to be natural or cesarean delivery, and it's quite difficult to assess the weight of the baby just before delivery due to lack of the amniotic fluid on US videos. So we have developed an end-to-end deep learning method for that, and Szymon will tell you some more details about it. And finally, the last main topic which I'm working on, my main topic of my PhD, is the non-invasive diagnosis of pulmonary hypertension. So the idea is that the gold standard for the assessment of pulmonary vasculature and for the assessment of the pressure inside of the main pulmonary artery is the invasive procedure, which is called right heart catheterization. And of course, we would like to avoid such procedures because they, of course, carry risk. So our idea with our collaborators from the University of Sheffield is that we could apply machine learning or deep learning methods to predict and evaluate the pressure inside the main pulmonary artery. We already have the paper published on ICCS regarding the prediction of the pressure in MPA from clinical data, and now we are moving more towards computer vision and the assessment of MRI videos of MPA. And that's all from my side.
Thank you, Michał, very much. Asia, please.
Hello, everyone. So my name is Joanna Kaleta, and I joined Sano in September this year. And the PhD project I am currently involved in is fetoscopic field of view expansion for twin-to-twin transfusion syndrome treatment. Twin-to-twin transfusion syndrome affects about 10% of multiple pregnancies due to placental vascular anastomosis. So when twins share one placenta and the same network of blood vessels that supply twins with oxygen and other nutritional values, one twin becomes a donor, which means he gives away much more blood, and the other one becomes a recipient, which means he receives much more blood. And this imbalance may cause several development abnormalities and organ failures for both sides. So to treat TTTS, the fetoscopic laser photocoagulation procedure is conducted to close down some vessels connections. And the challenge during this procedure is very limited field of view, and also very unclear field of view covered with various artifacts. And the main goal of this whole project is to create a visualization tool which will provide doctors with expanded and refined field of view. And now the project can be broken down to following topics. The first one is artifacts removal using denoising and inpainting tools, which is mostly generative models. And artifacts I am trying to remove can be, for example, laser pointer or fetus parts. So you can see them at the bottom of this slide. But there are also some other artifacts related to bed tool calibration or fluid turbidity. And that's and this topic. Of course, to test some approaches, I'm going to use data augmentation created by Tomek Szczepański and Szymon Płotka in the previous months. And this topic is something I am really focused on right now. The next topic would be placental vessel segmentation, which is partially developed by also Szymon Płotka and Tomek Szczepański. This is pretty straightforward task, but it would be extremely useful for the doctor to locate the connection that needs to be closed down. The third topic would be creating a whole pipeline consisting of data filtering step, denoising step, and finally mosaicing step to expand the field of view. And the last topic would be creating a 3D placenta visualization based on 2D fetoscopic images. And for that step, we would ideally use data provided from 3D placental model created by Przemek Korzeniowski. And this step is only in the planning phase right now, but we think it would be really great to have this visualization, which could reflect some real distances between different vessel connections without image distortions. Yes, and for now we have access to 2 data sets. Unfortunately, I can't see these points on the slide, but the first data set is publicly available, and it's called FETREC. And the second one is a data set from Bielański Hospital in Warsaw. And as far as I know, Szymon Płotka was responsible for gathering the data. Yes, and that's all from me for now. Thank you.
Thank you very much. So I will just add that we have ambitions to actually run a test system and conduct validation studies at Warsaw Medical University. All right, Tomek, please. Tomek, are you there? Or maybe you need to unmute.
You have to unmute.
Sorry, I forgot to unmute my microphone. You can hear me now, yes?
Yes.
Okay, thank you. So my name is Tomasz Szczepański, and I have been in Sano for 6 months. And my academic supervisor is Professor Tomasz Szczeciński from Warsaw University of Technology. And my PhD topic should be broadly understood as orthodontic treatment planning. But to be more precise, it is in fact an attempt to create any method that can help the orthodontist. And in this project, I collaborate with 2 orthodontists, Professor Piotr Fudalej and a doctoral student under his supervision, Arleta Adamowicz. So on the basis of the data in our possession and the review we have carried out so far, we set 2 instance segmentation as our first task. It will be performed in 3D and based on the cone beam computed tomography scans. The segmentation is an essential step for most treatment planning methods and a starting point for us for further research. An accurate segmentation may also already be material for the publication, and this project is underway. So let me move to the next project. We can see a promising future research direction, which is a 3D tooth reconstruction. The CBCT scan faithfully and accurately depicts the entire tooth, the crown, and its roots, but unfortunately, it is an expensive procedure and a source of high doses of ionizing radiation. So therefore, we propose to reconstruct the 3D scan. We are aware of possible loss of information during reconstruction, but we plan to restrict reconstructed data used to the cases for which the quality of the reconstruction will allow its use, and we will consult it with our clinical collaborators. And we will, for the reconstruction, we will use 2D panoramic radiograph, and such attempts have been made so far. But we want to leverage also information from an 3D intraoral scan performed with non-ionizing structured light, and the task will be solved with using generative deep learning methods. And now I will move to the last part of my slide. During my research in Sano, I collaborated with Szymon Płotka and created data augmentation algorithms for fitoscopy endoscopic procedures Joanna talked about already. And the purpose of the created methods is to overlay various effects that closely mimic the artifacts present in the data set, such as, for example, optical fiber structure or particles floating in amniotic fluid, and all of which negatively affect the quality of the image. So training the model on such an augmented data set not only improves the accuracy, but also importantly, minimizes the generalization error on previously unseen data. That's all for my part. Thank you.
Thank you. And Paweł, please.
Hello, my name is Paweł Rent, and currently I'm involved into 2 projects at Sano. The first one is application of bike clustering in the analysis of biological and medical data. And this is something that I'm working on with Patryk Korzeniowski from the University of Pennsylvania. Bike clustering is the most suitable for bioinformatics, more precisely to gene expression arrays. And the problem is as follows. We try to retrieve subsets of genes and subsets of conditions under which they were measured and the genes co-regulate, in which the genes co-regulate or co-express. And this is on the right hand side of the slide. There is an example of such a data set. This is an optimistic case scenario because usually genes and conditions order doesn't matter. So the problem is very complex. And that's why we apply here heuristic algorithms. And yes, we try to cluster these genes and conditions at the same time. And yes, the second project is more related to classical machine learning. This is a collaboration with Professor Tomasz Guzik from Glasgow and his team. He's also affiliated with Jagiellonian University. And here we have data sets of patients and their vascular features, and we try to establish phenotypes of their diseases. There is a subset of patients that are in their early hypertension and that do not have any hypertension, and we apply some basic methods like dimensionality reduction, like t-SNE, UMAP, or FATE. And also we cluster it, we make some regressions off of it, and then we compare the subgroups in order to localize some phenotypes. Recently, we've submitted a paper to Hypertension Journal, and now we are waiting for the response regarding this. Thank you.
Thank you. And Szymon.
Hi, my name is Szymon Płotka. I'm PhD candidate at Sano and the University of Amsterdam. Today I'm talking about fetal birth weight estimation, or what Michał mentioned before. So fetal birth weight is a significant indicator of perinatal health prognosis and accurate prediction of fetal birth weight, as well as gestational age, complications in pregnancy, and maternal physical parameters are critical in determining the best method of delivery. So we have two types of methods. It's natural or cesarean. And fetal birth weight is a challenging task requiring highly visible fetal body standard planes, which can only be identified by experienced sonographers. And fetal birth weight provided by clinicians are often imprecise, with up to 15% in mean absolute percent error. And as data set, we use 300 2D fetal ultrasound video scans that come from 100 independent patients. Please note that this data set come from the last routine fetal ultrasound examination prior to 24 hours prior to delivery. And as real grants true, we have a real fetal birth weight after the delivery. So as solution, we propose hybrid neural network that consists CNN and transformer-based neural network. So it's a end-to-end framework for spatio-temporal fetal ultrasound video scans analysis that automatically performs fetal birth weight prediction. Important is that our method works without the need for finding standard plane in ultrasound video scan, which are required in the classical method of estimating fetal birth weight. We have a paper called BabyNet Residual Transformer Module for Birth Weight Prediction on Fetal Ultrasound Video, which we presented this work at top-tier conference called MICAI in Singapore. So in this slide, you can see our poster session, and I would like to invite you for more details based on my work in the next month, because I have my own seminar in December. Thank you.
Thank you, Szymon. And Kuba.
Hey, can you hear me?
Yeah.
Okay. My name is Korzeniowski. I've been in Sano for a month right now, and the title of my project is Haptically Enhanced VR AR for Improved Information Capture and Exchange in Medical Social Environments. So this project is conducted with collaboration in collaboration with University of Sheffield. And what we want to do is to produce a comprehensive end-to-end system in VR that can assist clinicians in browsing and exchanging information regarding patients and their tests and their results. So the doctor, for example, could enter this system, take notes through some browse through the basic information of the patient, browse through the test results, look through the images, and then probably perform some simulations regarding the planned surgery or the procedure. And also what we want to do and what is pretty important for us is to address two things. The isolation aspect, the social isolation aspect, so the doctor can interact with other clinicians and consult with them, and take at the same time take notes using his or her keyboard, and just to really go through this workflow of working with the data. And also we have some areas to explore. So what we want to do is to improve and integrate existing surgical simulations that are currently in place to probably develop some database that could be implemented in the VR environment with all this patient data. For this keyboard integration, we want to do AI solutions to detect and place it in the physical space, so it can be transferred into virtual reality space seamlessly without any interaction from the user. Also, regarding the image presentations in the VR, we want to explore possibilities of 3D image reconstruction from different images, for example, for blood vessel modeling. So that would be about this part. Przemek, if you could turn to the other slide. So I believe I have to. This one is also mine. Okay, so
yes, please.
This one is this slide tells is about augmented reality visualization for brain connectomes on tumor patients. So essentially, what a connectome is a functional map that describes how neural units of the brain are connected to each other, and what they can do is to predict and show the physician, the neurosurgeon, to be specific, how every interaction with the brain, so a cut of the scalpel, would, for example, affect this functional structure of the brain. And what we want to do is to use the AR environment to inform the clinician what it would do. So essentially assist in surgery. So as you can see, the basic visualization on the brain model is already implemented. What we want to do next is to perform automatic registration of this connectome map with the physical brain. So it would just overlay precisely and automatically. And then when this is done, we can think about tracking surgical tool and visualizing how the actions of the surgeon are gonna affect this connectivity. So that's it from me. Thank you.
Thank you, Kuba. Okay, now me. Remote examination room. So that was project ideated by the previous team leader, Arek Sitek, and I started developing it as a postdoc. So the idea is to take the telemedicine to the next level and be able to interact with the patient, examine the patient, or even touch the patient remotely. So the system is very simple. So it consists on two sides. So one side is a robotic arm, which is equipped with a 3D camera, and we can interact with it remotely via local network, Wi-Fi, or even 5G network using a VR headset or a haptic device. So here is the sort of purely visual version, visual examination, and here is the haptic version, which allows us to basically touch the patients. So at the top, at the end effector of the robot, there is a torque and force sensor, very accurate one, and basically the readings from the sensor are sent via network to the haptic device. So we plan to validate it this year with the clinicians, but we would like to take it to the next level and develop a system which would do, for example, remote ultrasound examinations. And there will be Karol Pustelnik starting MSc master project soon on this topic. And this is very interesting because it will be teleoperation system. So the clinician with a haptic device would do the remote ultrasound examination. But this will allow us to collect the data for fully autonomous or semi-autonomous system. So we would like to train basically what the robot sees, what the ultrasound probe sees, and how it should move in the next step. Okay, thank you. And we'll continue with robotics topic with Mr. Gogo. Emmanuel, please. Okay, Emmanuel, are you there?
We can't hear you, unfortunately.
So maybe Natalia will make a quick swap.
Yes. Sorry, some system error. Like I checked up, but it happened. So
yeah, it happens. Please go on.
Okay, so my name is Emmanuel. I'm PhD student in Sano. This my PhD project is assistive robotic caregiving, or in short, AR care. The goal of this project is to develop some assistive robotic caregiving system. You saw the robot and the system previously. It's basically equipped with minimum kind of sensors like 3D camera, force sensors, and those kind of things. Then the aim of this system is like it can be mounted on a hospital bed or wheelchair or some other like mobile basis, and to provide aids to motion impaired patients, such as it can be like feeding tasks, dressing, object fetching, or assistance to nurses or caregivers with patient-centered tasks or some other daily activities. So it's a kind of project that focuses in healthcare industry. So you might have asked like what drives us to do this project. There are some challenge from healthcare, like aging population, rising cost of healthcare, shortage of healthcare workers, or maybe people with disabilities and caregivers like prolonged stress, or some jobs like demand physical demands. So there are some objectives. Basically, we have two objectives in this project. These are basically the requirements from the systems. First requirement is the robot or the system should be able to manipulate some tasks or objects or some let's say food types. So the first thing is manipulation, and then the second thing is to interact with care receivers or patients. So we have two main objectives that we are developing here. So in the manipulation part, we deal with dexterous soft body manipulation. It can be different types of food that are like soft bodies. And then this kind of manipulation skills are designed for robot caregiving, such as scooping a food or folding laundry or some other daily activities. The second thing is to train AR care system to interact with care receivers, such as feeding, clothing on, or so on. So, okay, to do this thing, we need some to combine multimodal sensing and perception to develop intelligent planning and control policies for safe and efficient manipulation with and around humans. So yeah, we deal basically with safety because this system works with human and around human. So we deal with safety. There are three types of the safety we deal in this system. Okay, could you return back the slides? Okay, there are three safeties we deal in this system. In the development phase, there is safety called safe exploration during the testing, safe transfer, and then the long-term safety is called safe policy. Okay, next slide, please. Okay, safe exploration. We use reinforcement learning algorithm to come up with some intelligent policies to manipulate tasks, to manipulate some objects, do some tasks, or to interact with care receivers. So it's impossible to train these kind of things in a physical system. So we use some simulated worlds. So as you see here, there are, so these simulated worlds help us to safely explore. And then as you see here, there is our care sim world. We can build tasks from care devices, as you see here, below at the right corner, care devices, care avatars, and then with combining these two, we can create care tasks. And then there are some care sensing systems, DIPS sensor, RGB or color sensor, force sensor, those kind of things we can sense from this environment, and then we train the robot. And then after that, we transfer the trained model to the real world or to the physical robot. So here we come with a second challenge, safe transfer. So, okay, is it safe to try the online or the model that's trained on simulation on a physical world or with humans, like with real humans? No, it's not safe. We cannot guarantee to try this trained model on physical world or physical system. So in our safe transfer, we deal with how to test this system, transfer system in a physical world. Then for this, there are some advances in AR. We use some spatial awareness called. So that is just we have developed our solution in simulation, and then we build the simulation into the physical system, and then we are not directly going to interact or try on real human. We try on avatars using AR. In AR, there is a solution called spatial awareness. So that's to connect two worlds, the simulation world and the real world. Then lastly, we can test, develop, and we can test, deploy in real scenarios, maybe. Okay, could you play the video? Okay, could you pause it? Sorry. Okay, so as I said, we have mainly two objectives here. First, to train some manipulation skills for the robot. Second, to train how to interact with the care receivers. Then in manipulation skills, it's a skill to manipulate different objects with having different geometry. Then here I'll show you how the robot is trying to pick unknown object. Here, as you see here in column, there's scenario, sense, perception, how the robot understand the world, how the robot sense the world, then how the robot plan to pick these things. On the rows A and the B, there are different scenarios with different cases, robot with different future. And then the second B, robot with occluded, like the black object is like higher, a little bit higher, and then they're occluding the other things. So yeah, as we see, the robot is like picking these things. So it's basically trained on synthetic data of 40,000 scenes. And then from 40,000 scenes, there are 7 color and then depth information per scene taken from different camera perspective. Then the robot tries to pick like this. Okay, thank you.
Yeah, so we will get back to robotics topics later on. We'll switch now for VR simulations, also something about my background. So very briefly, I developed the spina bifida simulator. Spina bifida is a birth defect that is developed during early stage of pregnancy, in which there is an incomplete closing of the spine around the spinal cord. And yeah, we developed a prototype VR simulator for core manual skills training for fetoscopic spina bifida repair surgery. And we validated it at Warsaw Medical University on a group of 14 clinicians. And the initial validation study rated the simulator as realistic, and it recognized its usefulness as a training tool for fetoscopic procedures and learning of fundamental laparoscopic skills. So this work was presented 2 weeks ago at IROS conference, IEEE conference, top tier conference. And I have a quick, hopefully, video comparing real surgery to a virtual one. So here is a real surgical footage. So it's a placode diathermy. So with the diathermy tool, the clinician makes a circumferential incision around the placode, and here is our VR version. Then the tissue is pulled and dissected using scissors and grasper. So this is, of course, done in pregnant uterus. So it's a fetoscopic surgery. So it's done on a baby in woman's womb. So here's our cutting, and for the next stage of the project, we'd like to add patch suturing. Okay, and by using this the simulator, so as you may know, like for deep learning, we need a lot of data, and surgical data is especially difficult to collect and label. Like basically, surgeons don't want to manually label the data, and probably there is a big variety how they will actually label this. So this is very problematic. So we have like realistic VR simulation, we can easily generate synthetic surgical data, which is automatically labeled. And I believe that this is indispensable in the development of surgical vision algorithms, surgical assistance algorithms, and development of surgical robotics in general. And yeah, Sabina, you can.
So I'm Sabina, I am PhD student and I start in July. So I'd like to start by presenting my aim and scope of the research. So my topic of my PhD is deep learning by surgical robots, and the robot will be programmed to perform basic surgical tasks like grasping, needle manipulation, cutting. For this, I will use a combination of reinforcement learning and differentiable simulation. So below are the main steps to create project. So firstly is a robotic setup to generate appropriate motion of robotic arm. Second is observation and action space. Next one is exploration and reward. So I will prepare a training algorithm. So I will train using PPO and SHAG. SHAG is a neural method, and that can efficiently leverage simulation gradients, even in the presence of non-smoothness. It's being a 70 times reduction in training time over the best performing stabilization and reinforcement algorithm. On the last one is transfer to real world. So next, I will focus on deep reinforcement learning. It's a viable solution for automating robotic surgical subtasks due to its ability to learn complex behaviors in dynamic environments. So this task automation could lead to reduce surgeons' cognitive workload, increase precision in critical aspects of the surgery, and fewer patient-related complications. So training deep reinforcement learning methods using a virtual environment for robotics is crucial for real world use reinforcement learning due to impracticality of running millions of attempts on a physical system only to learn a low-level behavior. So on the right, you see article and about tissue retraction. So I will focus first on grasping tasks to do tissue retraction. Tissue retraction is a recurring subtask carried out during a minimally invasive surgery that involves manipulating deformable connective tissue to access the regions of interest, such as tumor, and takes a significant time during each procedure. So nowadays, minimally invasive surgery is commonly assisted via robotic platforms such as the Da Vinci surgical system that consists of several instruments. So since tissue retraction is one of the frequently used surgical gestures in the manipulated phases of surgery, it requires the surgeon to continuously switch between a robotic arm or coordinate with the assistant operator. So this protocol significantly increases the cognitive load of the surgeon and the risk of tissue damage. Hence, automation of this tissue retraction subtask can benefit surgeons by allowing them to focus on critical aspects of the surgery and potentially improve the overall outcome. So the significant protocol to perform some tasks in is to formulate the safety problems, for example, from issue retraction as set up properties that provide the limits of the safe workspace, such that the robotic arm does not collide with the surrounding automatically structures. It's my scope, so thanks as well.
Okay, great. Thank you, Sabina. Yes, so my transition to Sabina's slide maybe wasn't too smooth, so I wanted to add that we can use virtual reality simulations to train as a virtual training environment for surgical robotics. And basically, I tried this idea a long time ago. I believe there was something around 2016. But by basically running some state-of-the-art reinforcement learning algorithms like PPO back then on the simulations, but the results were quite poor. I didn't want to train on anything, especially using visual observations. But now things are different because we can run everything very efficiently on a single GPU. So we can run both simulation and learning on a GPU, which speed up things a lot. Plus, there is this new concept of differentiable simulation, which Michał will get into more details in a second. And our idea is basically to port our simulators in a differentiable way. So this way we'll have basically gradients in respect to the cost function when we modify simulation parameters or control. So Michał, please go into more, tell us a bit more about this. Thanks.
Okay. Hi all, my name is Michał. I'm working at Sano since July as well as Sabina. And I'm working on a project related to differentiable simulation. And when I'm saying simulation, I mean visually and potentially haptically realistic representation of surgical procedures. So it's all in the context of surgical procedures. And we want that simulation to be a fast and reliable representation of reality on computers. And this is a topic that is kind of well known, and there are many solutions available right now. But we want to add something new. And this new thing is using GPUs, so graphics processor units, which are very fast for some calculations. And we want to incorporate this whole surgical simulation environment within differentiable programming work frame. So I will say a couple of words more about this later on, but a possible usage for such a simulator is, for example, because there are obviously many, but first that comes into mind is teaching medicine students to perform such procedures in virtual reality. But this is also already a known topic. And another that we'll try to incorporate Sano with Sabina and Jan is to create a virtual environment for big scale learning, reinforcement learning of robotic arms that will be able, hopefully, probably at first only in some test environment, but they will be able to help with those procedures. And coming back to the things that we want to add. So I mentioned differentiable programming. So this is kind of cutting-edge technique that's implemented, for example, in NVIDIA in their warp environment. And this allows us to calculate within or while running the simulation in real time, to calculate derivatives or gradients with respect to the input parameters. And thanks to that, we are able to tell not only how much are we wrong with our prediction. For example, when a robot moves its arm, and when we want liver, for example, to be pushed 10 centimeters right. So usually we only know the actual distance that the liver traveled when this arm was pushing it. And thanks to this differential programming, we'll be able not only to know this distance, but also to know which direction should we modify the robotic arm movement in order to get to our goal. So we're not only able to know how much wrong we are, but also in which direction and how much do we have to move in order to be correct. So this is a big step that can really make learning faster for robots. And the other thing is using GPUs, as Przemek mentioned. Many machine learning algorithms are constructed or are performing very well on GPUs. So we can use that, and we can do both things on GPU. So we don't have to transfer data from GPU to CPU, which is very inefficient, but we can remain with our data on GPU and with our algorithms on GPU. So this will hopefully make things run faster. And incorporating all of that into one environment will allow us to create a virtual environment. For example, have 1,000 robotic arms running on our GPU or set of GPUs in parallel, and each robotic arm will try to move the liver for 10 centimeters, and it will have a response in parallel about how wrong it was, so we can improve, I don't know, 100, 1,000 times faster than in regular algorithms. And if you can change the slide, Przemek, I only have an example of what I've managed to accomplish so far. This is a model, a 3D model. It's kind of a raw model, so we can see the triangles, tetrahedrons. But this is just a first step. And this is a liver, model of a liver in an abdominal cavity. And the kind of gray bar you can see on the right-hand side is a laparoscope that drags part of the liver to the right-hand side. So it kind of looks realistic. Okay, so that's all from my side. Thanks.
Thank you, Michał. So yes, indeed, differentiable simulation is a brand new thing. So we are informally collaborating with NVIDIA simulation team who is behind NVIDIA Warp. So they are really interested in what we are planning to come up with. So obviously, for all these things to work in real life, we need to transfer this from real world, from simulated world to real world, which is a problem on its own. But the key to this is to have like the most realistic simulation possible. And Jan will tell us basically how to improve the real-time simulation with deep learning. Jan, are you there? Okay, so if Jan is not here, maybe
one moment, maybe I will check if he is not, if he hasn't joined yet. I can see him as attendee. So, Mateusz, if you just can move Jan to panelists.
Yeah, hi.
Looks like we are all set. So yeah, the floor is yours.
Okay, please. Yeah.
Sure. Sorry, maybe I logged the wrong way or something. In any case, hello everyone. I'm a postdoc at Sano at Przemyslaw Group, starting from September. And the postdoc project I'm currently working on mainly as trying to simulate graphics as realistic as possible. As we all know, simulating graphics is not that simple task as just adding numbers on or I know multiplying numbers on our computers. It is kind of a complex task, and we even have this mentioned GPUs to perform that task for us. However, as it and due to that fact, often the graphics isn't that realistic as it's supposed to be. And furthermore, what happens, well, we all know if you play Cyberpunk on PS4, then you know what can happen with graphics from time to time, and loss of FPS and stuff can happen. However, the idea here and this project is to, in a sense, train graphics before the real-time usage. So in a sense, to prepare graphics in the previous time, for example, I know on a supercomputer or somewhere else, and one may wonder, well, is it possible? And as it turns out that yes, and then what one does is one does this. We render roughly low resolution graphics, and then we add the deep neural network, in that case graph neural network. I will explain that in a moment why we want that to simulate the higher resolution simulation, to put it on top. And because forward propagation is much faster for the neural network than rendering high resolution graphics, we can get high resolution graphics at the moment when we need it, with far less cost as previously, especially when calculating physics. For example, when calculating what will happen to somebody's hair in computer games, this can be a game changer, because it requires massive computations, and deep learning allows us to do this computation in a sense before the real-time simulation. So we can spend as much time as we want working down in our labs coding stuff, and then we can get we can get real life simulation by making a low dimensional simulation and then adding a neural network that will improve the simulation into the higher resolution simulation with much less cost. Now, why the graph neural networks? So normally when, for example, looking at the pictures, we have certain resolutions, we have pixels and that have the same ranges between them. However, when we render graphics, we sometimes want something to have much higher accuracy. Again, a good example is here. Than the other parts. You can, for example, I know, imagine some opaque black thing that you don't want, that you don't need to concentrate in this. That then maybe a couple of pixels will suffice. Why, for example, for rendering hair, you need a lot of pixels and you need a lot of computing power. So this is why you need graphic neural networks that will have an adaptive mesh for your purposes. Because, for example, when you have a flat object, then it's or an object that have a not big gradient of colors, then you need much less dense mesh than you need, for example, for simulating hair or facial expressions. This is why we need graph neural networks, which enables us much bigger flexibility than the originally CNN neural networks that are used, for example, for objects classification and this kind of things, because we need bigger flexibility. But obviously it comes with a price of much bigger computing power that we need for that, and often weeks of simulations and things. Yeah. So that would be the so basically, my project will be slightly technical to the other projects, but the results could be used in much of the virtual AR, VR simulations and improve them. So yeah, that's the general idea. Thank you.
Thank you, Jan. Yes, so our plan is to first significantly improve both visualization and simulation quality of surgical simulations. So that for sure will improve the educational experience for the residents, for the clinicians, but will also make it smoother transition from simulated to real world for robots and other algorithms. And yeah, I mentioned that last week, 2 weeks ago, I was in the IROS conference, and there was a whole bunch of surgical robots demonstrated from different companies and universities, and everyone wants obviously to make them autonomous, and there is a definitely need from the community for simulation tools and reinforcement learning tools for surgery. Okay, and last but not least, Natalia, please.
Hi everyone, my name is Natalia Lip. I am a psychologist and my project is about trust. So as you heard, our whole team works on applying simulations and automation in the area of healthcare. So in some sense, my project is meta work because I want to increase trust towards such solutions. So let's start from some basic definition of trust, and then wonder if it is possible to achieve it in automated clinical settings. So basically, trust is a psychological mechanism to deal with the uncertainty between what is known and unknown. Trust is about allowing yourself to be vulnerable in a relationship with the other party. It means believing that other party is competent, concerned, reliable, and willing to help. Thus, trust implies faith in the second party's good intentions and readiness to disclose personal information. In our case, there are two aspects of trust worth concerning. First, whether clinicians will be willing to use automatic solutions and during diagnosis, and second, whether patients will feel comfortable during automatic examination. So I started my project with physicians' trust, and bad news. Old past studies suggest that physicians are not willing to work with AI. Their concerns are about legal liability, identity crisis, fear of being replaced. Actually, there was one study in which physicians were asked what they would do in the situation of conflicting diagnosis between their own and generated by AI. And most of participants answered that they would follow their own expertise, disregarding AI analysis. But it's not all bad, because the ugly truth about people is that generally people rarely behave the way they think they would. In other words, very often we can observe that actual behavior differs from our cognitive attitude. And this is my main assumption when I started thinking about this project. So in the first step, I wanted to check how physicians behave in a situation of conflicting diagnosis, whether they follow their opinion or whether they trust in AI analysis. But before that, I decided to firstly conduct a pilot study on general population, because I wanted to exclude some irrelevant factors, and by doing so, ultimately reduce the required sample size. So I conducted an online experiment with the participation of nearly 300 people from general population. And the experiment aimed to check how people behave in a situation of co-deciding. So there were two experimental groups that differed in terms of identity of counterpart. By counterpart, I mean a co-decider. So in the first group, the counterpart was another human, and in the second group, participants co-decided with AI system. During the experiment, participants were asked to read description of two art styles, Impressionism and Expressionism. After that, participants were presented with 6 art pictures, and the task was to decide whether a presented picture was created by Impressionist or Expressionist. At the same time, participants were informed about decision made by counterpart. So I showed my participants a clue given by AI or another human. And at the end, participants filled out a questionnaire on trust. Really, I would like to show you preliminary results. So they are quite promising. So we can look at violin plots on the left. This is reported trust to human counterpart and to AI counterpart. As you can see, people answer that they don't believe in AI clues. The level of trust to human is much, much higher. But please look at the plots on the right. They present level of compliance between participants' decision and clue given by counterpart. And there is no difference between those two plots. Basically speaking, it is as predicted. People say that they don't trust AI, they don't want to work with it. But when they are put in a situation of decision making, they are quite willing to follow clues, no matter from what source. So the next step is to change this art picture to ultrasound images and conduct this same procedure with participation of physicians. And for me, it's over. Thank you very much for your attention.
Thank you, Natalia. Thank you, whole team. Very well done, well delivered. So just to wrap up, we'll have a few more minutes for questions, but the last slide, just want to add that our team took in the last months, we did quite a bit of science communication and public engagement. So there was event for students, medicine students at our lab here on the top left. And we also took part in Noc Naukowców, a science night at Małopolska, and we joined Neo Hospital. So we took our simulator, took all our VR, AR, haptic devices in backpacks, and we set up there. So that was quite successful. I believe 600 participants in total. So big thanks to everyone involved, especially Sabina, Natalia, and Emmanuel who helped out with the events. So thank you very much. And now we are all open for questions.